Hi, welcome to another lecture on probability. Last time we talked about the description and the terminology that we use in this topic, and today we are going to go ahead and do several problems. So last time we talked about we have the concept of a trial or experiment that was like flipping a coin, picking a card, and so on. Then we had the sample space, which was a list of all possible outcomes. And then we talked about the probability of an event. A particular subset of sample space was called an event, and we talked about how to calculate the probability of that. Today we are going to go ahead and do some exercise problems. So, uh, first problem that we are going to take a look at is that we flip a coin 3 times. What is the probability of, now let me write this thing in parentheses, exactly 2 heads. So when we say 2 heads, somebody might think about, well, if it comes out heads 3 times, is that good enough or not? To make the matter clear, we say exactly 2 heads, so it means 2 heads and 1 tail. Now, what's the best way to go ahead and make our sample space here? First of all, when we talk about a coin, we mean a fair coin, so it has a equal probability of landing heads or tails. We could consider a rigged coin as well, but let's just go ahead with a fair and equal likely coin. A way of keeping track of what's happening is so-called tree. Tree is just a mathematical diagram that looks like a tree and helps us keep track of the event. So here's the root of the tree, and then we at this root we uh, flip a coin, and the coin can come out to be heads or tails. And then we do this thing again at each of this is called so-called node. We do this thing again, and it can land to be heads or tails. We always draw them in the same. Let me do this thing again. Heads or tails. Since we are throwing it 3 times, we do one more round. So we have uh, another branch here coming out, heads and tails, and then heads and tails. Gradually this tree becomes very crowded, but we just patiently draw this picture and heads and tails. So notice for sake of a pattern to emerge, we are going to do, for example, all heads first and tails next. Now we go to from the root through a branch all the way to the end, see what happened. First landed heads, and then heads, and then heads. So here I list the outcome if I go through that branch. So here's my outcome. Here I have heads, heads, and tails. Heads, heads, and tails. And then I have heads, tails, and heads. Heads, tails, and heads. And then I have heads, tails, and tails. So this was that branch, this is that branch, this is this branch, this one, next branch, and so on. So here we start with a tail, and then heads, and then heads. And then here I have tails, heads, and tails. And then here I have tail, tail, head, and this one, tail, tail, tail. Now, if you go ahead and count this thing, you see there are 8 possibilities. Not surprising, because first you have 2, out of each of them comes out 2, so by then it's going to be 4. Out of each of them comes 2 again, so doubles again becomes 8. So the numbers go through the following sequence: 2, 4, 8. So that is my list of all outcomes. So if the sample space is to be denoted, sample space, we said we draw a curly bracket, we list all these possible outcomes, separate them with commas to make sure they don't run into each other, and then so HTH, this item 3, and then HTT is the next one, and then THH is the next one, THT, and then TTH, and then TTT. So I was thinking of throwing this coin 4 times. You can imagine the next round of this will have 16 items. So every time it doubles, 2, 4, 8, 16, 32, and so on. So quickly it grows. Well, exactly 2 heads. Who are these? Let's just mark them. Exactly 2 heads. So this is a possibility. This is a possibility. This one isn't. This is another possibility. So exactly to probability of. So I can write probability of 2 heads in 3 tosses of a coin. So 1, 2, 3. There are 3 cases out of how many? So there are 8 cases. Probability of 2 heads in 3 tosses is 3/8. No, there are ways of doing this thing that wouldn't require drawing a tree with the formulas and such, but let's just understand what is meant here, and our shortcuts might come up later on. Notice if we had instead of coined, if we had the issue of gender in a birth, this could have been, for example, boy and a girl, and a boy and a girl, and so on. So instead of age, I would have had B's, and instead of tail, I would have had G's for the girls. So it would be exactly the same thing. Probability of having 2 boys in families of 3 kids, assuming that the probability of boy or girl is all 50%, for that one also would be 3/8. While we are at this stage, what is the probability of 3 heads? Probability of 3 heads. So while we have this thing, we might as well make use of it and answer a bunch of questions. Probability of 3 heads. I'm always assuming in 3 tosses of a coin. Of course, 3 heads just shows up once in the 8 cases. Similarly, probability of 3 tails. 3 tails, same as 3 heads, that's also 1/8. Probability of more than 2 heads. Which means what? Which means probability of 2 or 3 heads. 2 or 3 heads, so 2 heads, 3 possibilities, 3 heads, that would be another possibility. A total of 4, so 4/8, which you can simplify and write it in 1/2. So what's the probability of, let's say, no tails? So no tail What are the cases where there is a tail? Well, these are all cases where a tail shows up. No tails means, well, all, that's another way of saying all heads. So that's another way of just picking up the very first choice here, and that would be also 1/8. So it's same as probability of no heads. That's no heads means all tails. So these are all very similar kind of probabilities. Now remember that we had a demo for this. So we had this demo in this particular one, and the three coins are flipped, and now for example here we have all tails and so on. We are going to be counting how many heads show up. So for example, if I flip once, here I have, this is going to be read as H H T, and it showed up once. If I do another one, for example, it turned out the same thing. Here's another one. Again, we're just counting the tails, so this is going to read as heads, tails, heads, and this one is going to read as tail, heads, heads, and so on. So in 4 consecutive attempts, I got 2 heads and 1 tail, and let's do 10 of them so that we have the process done quickly. And then it says, yeah, so far we have done 14 attempts. In 7 of them, 2 heads were obtained. In 4 of them was 1 head, and then in 1 of them there was just 1 head, and so on. And then we can repeat this thing and see what kind of a distribution we get. In this would be an experimental distribution. Then we can compare it against what we obtained there in the homework that was a theoretical one. So what we have here, if we want to achieve the same thing in that demo, in that application that we had, then we have to run that demo many times, like 1,000,000 times, and then calculate the probabilities experimentally compared to what we have here, and then it will be the same. Let's go and take a look at another kind of an exercise, perhaps of the examples that we had here. So we said gender and birth order. That would be exactly like heads and tails, because there are 2 types of possibilities here. Let's go ahead and play with the case of a pair of dice. Pair of dice presents us with a new interesting problem. So when you have a dice, of course you can have one, and when you have a die, it's going to be one of these 6 cases. Is that right? You get either 1 or 2 or 3 or 4 or 5 or 6. So this is the sample space of a single die. So for example, what's the probability of getting a 4? What's the probability of this is happening? Well, the die has an equal likelihood of landing on any of these things, and we are assuming it's a fair die. There's no rigging in this thing. They are all equally likely. What probability of getting a 4 is 1/6, but that's same as probability of getting 1, or probably getting 2, or probably getting 3, and then same as probably getting 5, or probably getting 6. It doesn't make any difference. In all of them is 1/6. So it's kind of uneven, not so interesting. So Next up is a pair of die. So now we have a much more sophisticated situation. I can have 1 1, or I can have a 1. Now it's going to take forever to actually draw, and so on. So if you allow me, instead of drawing the squares and such, I'm going to just write the number that it landed. So 1 1. So this is not to be read as 11. It really means 1 1, 1 2, 1 3, 1 4, 1 5, 1 6. Okay, so let's arrange them like this. Again, this is really I have to separate them, but that's just going to make it more crowded. So we can get 2 1, 2 2, 2 3, 2 4, 2 5, 2 6. So let me put my commas. So what does that mean? You can have 1 2, for example. Let's, to keep our head straight, we can color our dice. So I can have a red coming 1 and a blue coming 2, or I can have the red coming 2 and then blue coming 1. These are going to be recorded as differently. So so I can have 1 2 and then 2 1. You can throw them in sequence and so on. So you can have also 3 1, 3 2, 3 3, 3 4, 3 5, 3 6, 4 1, 4 2, 4 3, 4 4, 4 5, 4 6. I can get 5 1, 5 2, 5 3, 5 4, 5 5, 5 6. Kind of tiring, but we are done. You can get finally 6 1, 6 2, 6 3, 6 4, 6 5, 6 6. Well, this is your sample space. Now you have to decide what are you going to do with this. Like if you get 1 2, what are you going to assign to that? If you get 6 6, what are you going to assign to that? We have plenty of choices. It depends on the rules of the game. How are you going to play? So one rule is to go after sum of dots. So when you get 1 2, you say I got 3, and this is also a 3. If you get 6 6, double 6, you say I got 12. If you got 1 1, you say I got 2. So if we play the game of sum of dots, then the following is going to happen. That well, if you get 1 1, what you say you got is that you got a 2. 1 2 or 2 1, you got a 3. 3 1, 2 2, or 1 3, you said I got a 4. And then of course this one I got a 5. And now this one, all of these numbers, 6. So 6 means I got either 1 and a 5, or 2 and a 6, or 3 and a 3, and 4 and a 2, or 5 and a 1, and that all leads to 6. The next round is 7. I can get 7 in 6 different ways. And then let's make sure we don't run into each other. And so this is I get an 8. This is I get a 9. This is I get a 10. This is 11. And this is of course a 12. So assuming that you're playing the game of sum of dots, what is the probability that I get a 4? So again, we are playing 2 dice. We roll them. The question is, what's the chance I get the sum equal to 4? Well, one, two, three cases in which I get a 4, and all of these are equally likely. Anything could happen. I throw one die once, I get something. Throw a second one, or pick the first one again and throw it, I get something. They are any sequence is going to be equally likely as any other one. Uh, but if I play the game of sum of dots, then, well, things are going to become interesting. Getting sum of 4, I have 3 possibilities. 3, well, out of how many? 6 by 6, this is 36 possibilities. My sample space, all this entire thing is my sample space. Probability of 4 here is going to be 3 cases out of 36. You can simplify it, for example, write it as 1 over 12. Same way, what is the probability of getting 11? Well, 11, only 2 ways of getting 11. Either you got 5 and a 6 or a 6 and a 5. So there were 2 cases out of 36. If you want to simplify, you can write that 1 over 18 and so on. So some of the problems with respect to the dice can be done in this way. You can imagine that if you have 3 dice, it's going to be even more crowded. Your table here, instead of having 36 items in it, is going to have what? 6 by 6 by 6 is going to be 6 by 6 by 6 is 216 different possibilities. So that's a very crowded situation, but problems become more interesting. Perhaps a couple of these problems, I put them on your homework. If you throw 3 dice, if you could throw 3 dice, what's the minimum you could get? Minimum is so let's do yeah. So if I have 3 3 well, here I should have said dice. 3 dice. What is the probability of getting a 4? Well, how can you get a 4 anyway? 4, you can get 1 and 1 and a 2, or you can get a 1 and a 2 and a 1, or you can get a 2 and a 1 and a 1. Few possibilities. So there are 3 possibilities out of what? There's 6 possibility for the first one, 6 possibility for second one, 6 possibility out of the third one. So 6 times 6 times 6. So here we were multiplying twice, but now we have 3 dice, multiply 3 times. This is 3 divided by 216. That's the probability of getting 4. How about a 5? How can you land a 5 if you throw 3 dice? Well, of course, you can get a 1 and a 1 and a 3. Is that right? That's a 5. Then, of course, you can get 1 and a 2 and a 2. Is that right? No, the first one you can land this thing 1 3 1, or you can land it 3 1 1. Okay, all of them are possible. You could also get this thing in 2 1 2, or you can land it as 2 2 1. So 5, probability of landing a 5. That means sum of your dots is a 5 in 3 dice. Well, we see 6 possibilities over a total of 216. As we increase this, the counting will become higher and higher, and it's going to become a bit more challenging to actually keep track of this. Let me remind you, we had a demo for that. Let me see. So This one allowing you to go as far as, let's see, yes, it lets you play with 3 dice. So these things can be as low as 1, as high as 6. So the sum of all 3 of them is going to be as high as 18. It's going to be as low as 3. You can't get a 2 or a 1 anymore, but here let's roll it once. Let's see. So I got 3, 1, 3. The sum of all of these things is 7. 7, well, I rolled it once, so obviously I just got it 1. So here's another one, 3, 4, 2. Total is 9. I got it that way, and so on. No, let's go and this triple dice, let's roll it 10,000 times. Let's see what happens. Okay, these are all possibilities. Now, what is chance of getting a sum of 4? Okay, sum of 4. Well, in this is an experimental version. An experimental version of it, I have 128 times it landed to be 4 out of 10,002 times. To make the numbers kind of round, let's reset this thing, and I'm going to throw it 10,000 times. So I have 10,000 experiments I have done here, and 4 landed 134 times. So 134 divided by 10,000, what is that? Let's go back, compare against what we got here. So probability of experimental probability, experimental probability in that demo, what was it? I already forgot. Was 128. No, 100. This was 134. So 134. Let's go back here. 100. I got 134 in 10,000 throws. So it's 0.0134, as opposed to 3 over 216, which is 1 over, of course, what is that, 72, and then 1 over 72, I can do it here on the calculator, 1 over 72, and I get 0.01388, etc. It goes like that. Notice how close they are. So that was a theoretical probability is 0.138888, and this one experimental probability, running that experiment 10,000 times, I get 0.134, etc. So you notice that it's a very interesting problem. So as a mathematical problem, it would be very interesting for you to find out how can you land 6, how can you land 7, and so on. As high as this thing goes, the problem becomes more and more challenging and more interesting to keep track of all the possibilities. How can you get, for example, how can you get a 6? Well, of course you can get a 6 by 1 and 1 and a 4. What are the other possibilities you can get a 6? So you can have 1 and 2 and 3. Is that possibility? Yes. Is that how about getting 2, 2, 2? Well, that's a possibility. Now, this 3 can show up in 3 different ways. This can show up in 6 different ways. This can show up just one way. Let me just help you to see how this how we keep track of it. Let me put the 7 aside for a moment. So 114, you can have it listed, or they can come down to you as 141 or 411. Your dice can land this way. 1, 2, 3 will be more crowded because you can have 1, 3, 2, or you can have a 2, 3, 1, 2, 1, 3, or you can have 3, 1, 2, 3, 2, 1. So this one you can rearrange it 3 ways, this one we can rearrange it 6 ways, and this one there's just one rearrangement. So if you want to figure out probability of 6, how many ways can you get a 6? 3 and 6 and 1, 3 and 6 and 1 makes 10 different ways. I could have this thing 10 out of 216, as opposed to experimental probability that we had here. It is 421 out of 10,000, as opposed to what we have here. So this one was 10 over 216. Let's write out what is 10 divided by 216, and I get 0.04629, etc. And experimental probability for getting 6 to get 6, we can run this little app, and that one for getting a 6 was what? 421. So it was 421 was 421 out of 10,000 trials. That's 0.0421. So you see that they're kind of close to each other. The experimentation and the theoretical case, they are kind of close. When is it that this becomes close to that? Well, instead of 10,000 times, if we do it million times, it comes closer. If we do it trillion times, it comes closer, and so on. So these are some basic examples. For the case of the cards, the problem can become more sophisticated depending on what kind of game you're after. If you want to calculate certain probabilities, it becomes more challenging. But some of the basic ones are easy, and you can read about, for example, the Russian roulette, which has 38 pockets on its wheel. There are 18 reds and 18 blacks and 2 green ones, and certain basic games there. You can calculate the probability of getting one thing or another. Okay, I hope you enjoyed this section. Until next time, good luck and God bless.